Hey guys, for today's topic, we'll be using nodal analysis in the S domain to solve a circuit problem. So what exactly is nodal analysis? Nodal analysis is the application of KCL to find a voltage drop through any component. So KCL states that the sum of the currents entering a node must equal the sum of the currents exiting a node. You also might be thinking, why would you change a T-domain circuit into the S-domain circuit? This makes the complicated circuit easier to solve for because capacitors and inductors can be essentially treated as resistors. This is done by taking the Laplace of each component, solving for the voltage, and then taking the inverse Laplace of the voltage to take it back into the time domain and get your answer. Notice essentially the spot that separates components away from each other. If we take a look at the right circuit in the uppermost corner, we'll see that the middle point separates these three components, that's just V1. If we take a look to the right, we'll see that we have to find the voltage going through the inductor, so we're going to want to take a node here too. So this can be V2. If we take a look at the bottom, we'll see that this whole area separates these three components from each other. Okay, so the next step is to identify the reference node. The reference node should be the node that separates the most components from each other. So the bottom node is essentially what we call a reference node. So we're going to set this as ground. The next step is actually solving our circuit. Okay, so the third step is finding initial conditions at time t less than 0, and this should be done in the t domain. So we take a look at our voltage source, we'll see that we have u of t. And let's remind ourselves that u of t doesn't actually begin until time 0. So we won't have any initial conditions, right? Our voltage going through the capacitor will equal 0, and the inductor current will equal 0. So the next part is taking our circuit and converting it into S domain at time t greater than 0. The voltage source will essentially change into 1 over S by using this table given below. So the Laplace of u of t is 1 over S. A resistor will be treated the same as a resistor. So this box right here is just 5. And this box right here is just 6. Of course, we still have our nodes, right? We're still solving for this V0. And this is still ground. So a capacitor in the S domain will be treated as 1 over CS, while an inductor in the S domain will be treated as LS. So this will become 1 over 0.01 S, while this becomes this is actually supposed to be 3.6. I apologize. .6S. Okay, nice. Just always remember that capacitors and inductors can be treated as resistors in the S domain. Okay. So the next step is using nodal analysis, right? So remember that nodal analysis is using KCL, so we're going to have to draw our current. So I'm going to label this current as going out of the node, out of the node, and this is going out of this node. So let's do our KCL at node V1. If we remember, current equals V over R. So we're going to take V1, that's at the start of the arrow, minus 1 over S, divided by our resistor, right? 5. That's coming out, and so is this middle thing. So we're going to say plus V1 divided by 1 divided by 0.01 S. We also have the other current coming out, so it's plus V1 minus V2 over 6. And if we simplify, we get 0.3 S squared plus 11S V1, because we're taking all the components of V1 and simplifying them, minus 5s V2 equals 6. So let's take a look at node V2. We'll see that there's a current coming into the node that is V1 minus V2 over 6 is equal to the current coming out, V2 divided by 3.6 S. So simplifying, we obtain that 3S V1 equals 3S plus 5 V2. Solving for V1, we get 1 plus 5 over 3S V2. This makes the math easier because we have two equations, two unknowns, and we're trying to find V2, right? Because V2 is going to be equal to the voltage drop through the inductor. So we're going to essentially plug this in to this equation and obtain V2. So if we plug it in, we will see that 0.3s squared plus 11s times 1 plus 5 over 3s V2 minus 5s V2 equals 6. We're gonna simplify more and say that 0.3s squared plus 6.5s plus 55 divided by 3 V2 equals 6. Solving for V2, we obtain that it is equal to 6 over 0.3s squared plus 6.5s plus 550 divided by 9. If we pull out the 0.3 away from the s squared, we get V2 equals 20 divided by s squared plus 6.5 divided by 0.3s plus 550 divided by 9. And to solve for this equation or this denominator, we're going to use quadratic formula, negative b plus or minus square root of a squared minus 4ac all over 2a. So we will get that V2 equals 20 over s plus 3.33 times s plus 18.33. We have to use partial fractions, so we're going to get equal to a over s plus 3.33 plus b times s plus 18.33. Using the cover-up method, by multiplying s plus 3.33 and setting s equal to negative 3.33, we obtain that a equals 1.33. And if we multiply by s plus 18.33, set s equal to negative 18.33, we obtain that b equals negative 1.33. So plugging in these values, we get b naught of s equals 1.33 divided by s plus 3.33 minus 1.33 divided by s plus 18.33. And then taking a look here, we see that this is going to match this Laplace, right? So 1 over s plus a is equal to e to the negative at times u of t. So we will obtain, so taking the inverse Laplace of this, we will obtain that v naught in the t domain is equal to 1.33e to the negative 3.33t minus 1.33e to the negative negative 18.33t multiplied by u of t. Okay, and just a quick summary. We know that using nodal analysis in the S domain makes any complicated circuit easier to solve for. So the first step is identify the node. Second step is identify the reference node. Third, initial conditions at time t less than 0 in the t domain. Step 4 is to solve in the S domain at time t greater than 0. Fifth is using nodal analysis, and then sixth is converting back to the t domain. I hope you guys liked this video, and thank you for listening.